How do you explain Einstein's scientific contribution to a layperson? Total layperson, no great scientific background. Everybody knows the formula. Yeah, MC squared, Einstein. How do you explain it?
Well, this is what I do for a living.
Okay.
And the answer is, if you want to understand the theory of relativity, there are two simple concepts. And if we can understand these two, we can make sense of the whole theory. They are covariance and invariance. Now, on Zoom, it's a little odd because it's not clear which way the picture is flipped. In real life, this is easier. What I'll do is I'll hold up a pen in my hand like this. And I'll say, okay, is the pen to the left or right of my hand? Now, in real life, you would see the pen as being to the left of my hand. I see the pen as being to the right of my hand. Well, we disagree. You say left, I say right. Which one of us is correct? Well, we're both correct, right? It depends on where you're standing. Now, if someone was standing where you were standing and said to the right, you would be wrong. So it's not that it's subjective, it's relative. It's relative to your perspective. So that's a covariant truth, something that varies with your reference frame. On the other hand, there's what we call invariant truths. If I ask, is the pen between my hands? Now, yes, that's true no matter where you're viewing from. That's an invariant truth, right? It doesn't vary with perspective. So in physics, what's important is separating the covariant, the frame-dependent truths, from the invariant, or what we think are the real truths, right? The idea is that if it's true no matter what your perspective is, then it must be true of the underlying universe itself. Now, in Newton, who gave us the theory that came before Einstein, we had a number of things that were invariant. That is, we thought were real things in the universe. Space, time, mass, these didn't change. So what I'll do in the classroom often is I'll ask a student, okay, how long do you think this pen is? And they'll say, we're in America, so we use the non-metric system. They'll say something like 6 inches. Say, okay, and then I'll walk across the classroom and say, how long is the pen now? Well, 6 inches, just moving across the classroom. And I'll go up to a student, we'll compare watches. If I synchronize your watch with my watch, 1 second on yours is 1 second on mine. If I then walk across the classroom, if they were synchronized once, they should still be synchronized. So we thought space or length, time, duration were real things. They were invariant. What Einstein's theory says is actually not. If I move at 3/4 the speed of light across the classroom, what you measure, well, what I measure as a 6-inch pen, you will now measure as a 4-inch pen. Well, is it really 6 or really 4? Which one is it really? Well, there is no really, just as there isn't, well, is the pen really to the left or right? It turns out that length is covariant. And similarly with time, the faster I move, the slower you will see my watch going. But to me, it's keeping exactly the same time. So length and duration, which we thought were invariant, we thought they were just truths of the world, turn out to be like to the left of or to the right of. They are covariant truths. And that's true of mass as well. The faster you go, the heavier you get. This is why you can't move faster than the speed of light. It's not an engineering problem. It's not that we haven't figured out how to do it. You can't move faster than the speed of light. Why? Well, as you approach the speed of light, your mass approaches infinity. And if something is infinitely heavy, how much force would you need to accelerate? Well, an infinite force, which means you need an infinite amount of energy. You can't get that. So the idea is that because these things are turned from invariant into covariant truths, they're truths that hold in a reference frame, but not between reference frames. And Einstein gives us equations that tell us how to translate between reference frames. So every reference frame is valid for describing how the world is, what we realize is that the things we thought were real turn out just to be artifacts of our particular perspective. Now, there is an invariant property in the theory, and this was actually figured out not by Einstein, but by a man named Hermann Minkowski, who was one of Einstein's teachers, whose class he always would cut in college. Minkowski read Einstein's work and thought, wow, this is brilliant. Isn't it funny? There must be another physicist named Albert Einstein, because that lazy guy who never showed up in my classes, he couldn't have done this. Well, it was him. And it's from Minkowski, who would then make fun of Einstein, saying things like, Albert Einstein's not very good at math, and I know because I taught it. It's not that Einstein wasn't good at math. This was his old professor whose class he cut, just razzing his old student. We've taken that and mythologized it and turned it into Einstein wasn't good at math. But what Minkowski pointed out was that the invariant, right? And remember, if it's invariant, that means it's part of the underlying reality, is that while length may shrink and time may stretch, they compensate each other in a way that a four-dimensional measure, a measure of space and time combined, turns out to be completely invariant. And if invariance means real, what Minkowski realized Einstein had showed us is that we live in a real four-dimensional world. And so that really is the interesting underlying sort of reality that we get from this really bizarre theory.